Good afternoon. Thank you for coming to hear about Mark Levinson. I'd like to begin by giving a very brief history of the brand and then talking a little bit about the current design philosophy at Mark Levinson. And finally, I'll be going over some technical details of our new 5800 series of integrated amplifiers. So as we go, if you have any questions that come up, please feel free to ask. I'll also be available afterward. And certainly, if you're attending the show, come visit us. So a brief history of Mark Levinson, the brand. So it was founded in 1972 by a person named Mark Levinson, who was himself a musician and a serious audiophile. And it was always conceived of as being the best. That was always the goal, to get the best sound. Of course, in 1972, transistor hi-fi equipment was not always the best sounding, but Mark Levinson equipment was always regarded as the best of the solid-state equipment. A few of the more memorable products. 1972, the very first one that was the very first product developed was the LNP2. This was a preamp and designed by an engineer named Dick Berwin, who has been in the industry for a very long time. 1974, you'll notice, here's the JC2, which is a much simpler design. JC for John Curl, another extremely well-known engineer in the audio business. I would say arguably the most famous of the Mark Levinson products was the ML2. So this was a 25-watt mono Class A amplifier, which, as you can see, was enormous, but was considered by many people to be the finest sounding amplifier in its time. It, as you can see, stayed in production for many years, was very popular. Later on, 1987, you'll see here's the number 23. This was a dual monaural amplifier rated for much higher power Class A-B operation. Later on, you'll see 1991 came the number 30 and 31, so this was a CD transport and digital to analog converter. Many of our loyal Mark Levinson customers still own these products. They had great longevity, very good reliability, and still sound good to this day. And I would say, arguably, the next amplifier that Mark Levinson is best known for was the number 33. This photo really does not do justice to the amplifier. It's probably about the size of this podium, but much heavier. It was constructed on the pallet that it was going to be shipped on, because once it was built, it was too damn heavy to move. But the technology in it was new and groundbreaking. The sound quality was fantastic, and these amplifiers are still in service around the world. 2000 was a big year. This was when Mark Levinson and Lexus entered an exclusive partnership, which still exists to this day. Mark Levinson is the only high-end brand in Lexus, and Lexus is the only car brand in which you can find it. Fast forward to 2014, this was the launch of the 585 integrated amplifier. So this was the first product which I oversaw the engineering of. So this was, because it was an integrated amp with a built-in D-to-A converter, was a new type of product for us, but also it was the work of a new engineering team. To give you a little bit of background, so I joined Harman in March of 2013. In October, we opened up this very beautiful new engineering facility. There's a team of 12 engineers there, and we work almost exclusively on Mark Levinson products. And it signals a big change in how Harman has been treating the Mark Levinson brand. They're very serious about investing in the brand and, of course, supporting the brand for its use in car audio. You see here this comment, unprecedented number of new products in development. We've launched 8 new products in the 500 series, and we're launching another 3 in the 5000 series, which is what I'll be talking about later. The design philosophy that we're currently using in our group, we refer to as Pure Path. And the analogy that I like to use, this is one of my favorite quotes. Albert Einstein once said, "Everything should be made as simple as possible, but not simpler." So we have tried to simplify the signal path. We've simplified the gain structure of the amplifiers, but we haven't gone to extremes. You don't open a Mark Levinson amp and find one transistor inside. That's too simple. However, you don't open it up and find 5,000 transistors inside either. It's about doing things intelligently and doing our best to make the right decisions for good reliability, for good sound quality, for good measurements. And that leads me into the first principle. What we say is science meets art. So yes, we look very carefully at measurements and we place a lot of faith in measurements, but we also listen to the equipment. And if the equipment doesn't sound right, it's not ready. Conversely, if it doesn't measure right, it's also not ready. Everything has to be perfect. The next point you'll see here, discrete direct coupled circuitry. So we don't use DC blocking capacitors in the signal path. They leave their own imprint on the sound. And the best way to not have to worry about what a capacitor sounds like is to not use one. So we use them very sparingly to take care of compensating the power amplifier for stability, for example, but not in the signal path. We design all of the audio circuits to be very linear without feedback. They have to work very well without it, and then we apply a small amount so that we can get more consistent behavior from one unit to the next. We can improve our specs, and we also use it to tune the sound of the amplifier. Our feeling is that a little bit of feedback sounds good. No feedback has its own particular sound. A lot of feedback has its particular sound. We prefer to be somewhere in the middle. Finally, we talk about highest quality components. If you go inside a Mark Levinson amp, preamp, any product, you look at the components that we use. As an example, if a resistor is operating at 0.5 watt, we use at least a 1 watt rated resistor in that location. This lowers the operating temperature, it enhances the reliability and the longevity of the unit, and it sounds better. If things aren't heating up and cooling down rapidly, there's actually measurable distortion that doesn't happen. So a quick overview of the 500 series. There are 2 integrated amps in the line now. The 585 was what we launched initially. Integrated amp with DAC. The 585.5, we added a phono stage to it. So that's a very complete integrated amp. The preamps, there's a 523 and a 526. The 526 adds digital inputs. 523 is analog only. Our 2 power amplifiers in the line, there's a 534, which is a 250 watt per channel dual monaural amplifier, and the number 536, which is a 400 watt monoblock. Both built very similarly. but of course, two channels of audio, one is a single channel. Our 519 is a digital audio player that we think of as a sort of a Swiss Army knife of digital music players. It plays actual CDs, those shiny things that nobody seems to know about anymore. Will stream content off the internet. Any of the premium streaming services, Tidal, Deezer, Qobuz, will play off your home network, will play off a USB drive, you name it, it will play it back. And finally, we partnered with VPI, and we released the number 515 turntable. As you can see, a number of components look very much like a VPI turntable, and there are a few components that are really unique to the Mark Levinson product. This was a very positive collaboration with them. They've been great to work with, and there are things that we did at Mark Levinson to tune the sound of this to make it sound like a Mark Levinson product. It's available without a cartridge or with an Ortophone cadenza bronze. So that's the little historical overview. What I'd like to do now is to discuss our new products. About 2 years ago, we set out on another development, and in this case, it was a new set of integrated amplifiers, new price points, new features, and we're just going into production now. So it's been a very long process, but a lot went into it, and I'd like to share some of what we did with you today. Of course, when we embark upon a new project, there's all kinds of features that we're told the unit must have. So there's an analog plus digital version and a digital-only version. We wanted to have in the digital version 32 192K capability, double-speed DSD, full MQA decoding, and we also offer a Bluetooth input. Not because Bluetooth is the greatest sounding medium ever invented, but it's probably the most convenient. And we want people to be able to enjoy music. And we don't want to editorialize and say, well, Bluetooth doesn't sound good, you shouldn't have it. No, enjoy it. We'll make it sound as good as we can. We have a full phono stage, choice of moving magnet or moving coil inputs, and of course line level inputs. You can see a number of control possibilities, Ethernet, RS-232, 12-volt triggers, all the features that these units really need to have to be competitive. And the power amplifier is 125 watts per channel at 8 ohms, class A/B. This was what we set out to design, and this is actually a rendering. This is from our industrial design department, and you'll see the end product looks frighteningly similar. Oh yes, I forgot to mention, this was our retail price target. So these are US prices. The digital only, $7,000 US. The digital plus analog, 5805, $8,500 US. So this is about half of the cost of our current integrated amp. So a big challenge. So what did we do? We remembered this. So I keep coming back to this. We have to make everything as simple as we can make it, but not more than that. How did we take that to this product? Well, in a couple of ways. So first of all, if you simplify a circuit, it reduces the number of components, which in turn reduces the amount of circuit board area that it occupies, and those make it less expensive. In the case of the metal components, we specified some less labor-intensive finishes. Still the same high quality material. There's 25 millimeter thick aluminum on the front panel, beautifully finished, but in a less expensive process. There are two, as an example, there are two side pieces on the front panel. Instead of making them differently, they're the same piece. Take one, rotate it, and it becomes the other one. So it's things like this that we did to simplify it without making it cheap. And last, something that many people don't even think about, we specified new test equipment for our contract manufacturer, and this not only allowed them to measure the units more accurately, but it runs the tests probably twice as fast as the old test equipment did. So less time spent testing means that we can still test everything just as thoroughly, but the manufacturer doesn't charge us as much for test labor. So no penalty in quality and a big reward in the cost. So these were our goals. We started with nothing, clean sheet of paper. So nothing that we had done before. Sure, we learned when we did the work on the 500 series, but we didn't reuse anything. The other thing that we did, you see, approached the design of these products not as two integrated amplifiers, but as a complete platform. So in other words, there's a circuit board with the phono stage and the line stage, a circuit board with the D to A converter, the amplifier assemblies. We designed each one of these individually so that they could stand on their own, which means maybe we can use them in a future product. Or we put them in the same box and they work well together as a complete system. But here was the final challenge that I gave to our engineers, was that the 5802 and 5805, when not being horribly punished or abused, but being used within their limits, should perform as well as the 500 series components, which are, as we saw, about twice the price. So that's a big challenge. So, big challenge number one, they have to perform as well. The rest of the challenges, design these products to be simpler. How do we make them simpler? We innovate. We don't just throw things away, but we come up with new ideas. Think about different ways of manufacturing, different circuit topologies, whatever we can do to simplify them, but make them better. So, off we go. We begin the design process. I put up just a couple of engineering drawings so you can see how we progress. These are some SolidWorks illustrations that are based on the renderings, but this was our first attempt at how are we going to package everything inside the amplifier. There's one of these awful Excel spreadsheets that, of course, we have to do because we can't wind up at the end of the project development with something that costs too much or too little. We get in a little deeper. This is the output of our CAD system. This is the layout of our digital audio board. So our D to A converter chip is here, and discrete output stages are here. And this is a whole lot of figuring and going over the design to make sure everything's right. But let's talk a little bit about how did we economize on the assemblies. So instead of having lots of individual circuit boards, we took basic functional blocks and combined them. So that saves money because it's fewer circuit boards that a manufacturer has to build. You'll notice here, these power devices are surface mounted and they have these large copper areas to act as heat sinks. So this is a very effective way of cooling the devices. It's not expensive. because the assembly here can be automated. Is it quite as impressive looking as these manually assembled heat sinks from a 500 series product? Maybe not, but it's just as reliable and much less expensive to build. We also, whenever possible, place components just on a single side of the circuit board. Brings costs down dramatically over placing components on both sides. As much as possible, we use surface mount. And finally, you'll notice that the circuit boards have a green solder mask. Less expensive, works just as well as the black solder mask. And since there's no change in performance, better to save a few dollars on something that won't be seen as often. Now the next challenge, of course, is we did all these things to take cost out. Where were we not willing to compromise? So we're not willing to compromise on the materials in the circuit boards. These are all gold over nickel plated circuit boards. They're compliant with all the environmental directives, and they frankly work better, they solder better. You'll notice here we have through-hole electrolytic capacitors instead of surface mount. They have much better life expectancy, higher quality. So yes, it adds some expense to the assembly, but it's for a good cause. We still continue to over-specify components, as I had mentioned earlier. Use a 1 watt part where you need half a watt instead of running everything at its limit. Use the best quality parts, but only where they matter. So we'll use thin film or military resistors, for example, in the phono EQ stage where we want it to be very accurate, or in the feedback networks where we want things to be extremely accurate, low distortion. As I mentioned earlier, we keep coupling capacitors out of the signal path, everything direct coupled with servos to get rid of DC. And finally, our transformer that powers the unit has separate windings for the left and right amplifier channels, so honest to goodness dual monaural operation. So to talk briefly about the individual assemblies within the unit, this is the amp channel that was developed. The power supply components are built directly on the circuit board that has all the output devices. The output devices are biased into a class AB, but a high bias AB. So they're running up to about half a watt of class A, which, although doesn't sound like much, probably 80% of your listening is done at half a watt or below. So it's significant. Even so, the output stage is designed for 500 watts at 2 ohms. Now, we're not allowing the amplifier to do that, but it could if it had to. Again, this is about better reliability, better sound quality. The voltage gain circuitry, which you see on this top board, is directly descended from the number 534. Imagine that you took a 534 and put it in a crushing machine and pulled a few things out, and it would look something like that. They work very similarly, similar sound between these amplifiers as well. And finally on this board, protection circuitry to monitor DC levels, to make sure that the output current isn't too high, to monitor the temperature, because these things are important. We want to protect the amplifier, we want to protect speakers, and of course we want to protect whoever the person is using this. Many more features. As I mentioned, a lot of these are descended directly from the 534. It's a unique topology for the input stage that has a circuit that cancels distortion without feedback. It's based on our folded cascode topology, which is, to explain it very simplistically, 3 transistors connected together to do the job of 1. But imagine that that 1 transistor is like the most fantastically wonderful transistor you ever used. So 3 doing the work of 1 doesn't sound simple, except in this case, the 3 are necessary to do the work of 1 better than 1 could do it by itself. So I talked about low negative feedback. What are the benefits of that in this amplifier? So the output impedance, which is the inverse of the damping factor, if you're familiar with that term, it's nearly constant from 20 to 20 kilohertz. Amplifiers with lots of feedback tend to have very high damping factor at low frequencies and very low damping factor at high frequencies, which causes some interactions with most loudspeakers. So this is very capable of driving difficult loads, has a very neutral sound. The distortion components that we do have are almost entirely second and third harmonic. So there's none of these 5th, 7th, 9th, 11th harmonics that can sound very harsh. And finally, it's got this wonderful, huge, deep sound stage. And that's one of the things that has always struck me about Mark Levinson equipment, because although I've only been with the company 6 years, I've been a fan of Mark Levinson equipment for more than 30 years. And I'll never forget the first time I heard it. There was nothing that sounded like that before. So the group, the engineering group, and I are trying very hard to keep that experience alive and make it better if we can. This is our digital audio board. We're using the one of the XMOS USB digital audio receivers. It's able to process signals up to 32-bit 384 kilohertz or quad speed DSD. It's also powerful enough to do the MQA rendering and decoding. The D to A chip is from ESS. That is their 9026 Pro. So it's their latest generation. Extremely low jitter, 7 choices of digital filters. Measurements are phenomenal, great dynamic range, so forth. The discrete analog circuitry to do the current to voltage conversion, this is a new design for us. Simplified from earlier work that we've done. However, one of the features it has is it's like the circuitry in our preamps. This has been designed to directly drive headphones. So both the integrated amps have headphone jacks on them, and instead of having a separate headphone amp or, God forbid, an integrated circuit for a headphone amp, we've eliminated all of that, and the line stage and the I to V converters are robust enough to directly drive headphones. And finally, you'll notice 4 large regulator devices over here, so 2 for each channel, dual mono, and multiple power supplies for the DAC chip. A little bit of detail. So we're using the XU216 from XMOS. It is a 16-core processor, which is just a phenomenally, stupidly huge amount of processing power. But it's necessary for MQA decoding, for upsampling, and all those other things that we're doing. The 9026 Pro, as I mentioned, has multiple filter choices, their jitter reduction circuitry, and it actually has it has 8 balanced 32-bit cores in it. So we're using 4 pairs of DACs per channel, added and differenced with each other to get stereo operation. But by using all of those in parallel, distortion's very low, dynamic range is enormous. We're also making use of the volume control that's built into the DAC chip itself. They say it has 127 dB of range. We're using about 80 dB of range. But because the DAC has 32 bits, even if you throw away 16 of those bits, you still have 16 bits of resolution. So the volume control really sounds quite good in the DAC. Finally, we're running 5 individual separate regulators for different features on the DAC chip itself. Here's our analog board, which is in only the 5805. All of the phono circuitry is here in the center of the board, closest possible to the phono inputs. It's a combination of integrated circuits and discrete transistors. The moving coil head amp down here is all discrete. The moving magnet stage and the RIAA EQ, we're combining some discrete JFETs with some audio op amps. And this is one application where the op amps really work pretty well because we need a lot of gain. So we can live with the fact that the op amps, by their very definition, have a lot of open loop gain. We don't need to use a ton of feedback because we need the gain. The other thing, like our 500 series products, we have individual signal relays for each input. So whatever inputs you're not using are completely disconnected. And whichever one you are using, we connect the ground and the signal together separately. We're using a digitally controlled resistor network. We're using it in a proprietary configuration. In fact, we've applied for a patent. I'll talk about that in a little while. But it's a very simple circuit. It's one differential gain stage with this differential resistor network around it. And again, like the digital audio board, you see 4 regulators, so two per channel for complete dual mono operation. All right, is everybody ready to get a little bit of technical stuff? Everyone have IV bags of coffee and whatever you need? We'll try to make it interesting. So this is what I would call a typical implementation of our volume control in the 5805. It's not how we do it. This would be what's in the data sheet, for example. So this resistor network is integrated onto a chip. It has a feedback resistor, it has a series resistor, and then this shunt resistor to maintain a constant input impedance. The way most people would implement this, there'd be an op amp for the non-inverting input, another one for the inverting input, and then 2 more op amps to combine the outputs of these to realize a balanced input, balanced output. So 4 amplification stages plus this volume control chip. To go over this briefly, because time is limited and I don't want to put everyone completely to sleep. Here, the signal at this point is a direct function of whatever's at this input. Signal at this point is a direct function of whatever's on the inverting input. We then difference these to get our balanced output. So these outputs, equal voltage and opposite polarity. Over here, these may or may not be balanced signals coming in, which means these may or may not be balanced signals, which is why we need this whole set of 4 gain stages. 4 gain stages, though, not very simple. So we've done this in a completely different fashion. We use the same resistor network with one gain stage. So this one gain stage has balanced inputs, balanced outputs, and in order to get the best performance out of it, we're using this amplifier connected at what engineers call a bootstrap. Where the expression comes from is the circuit pulling itself up by its bootstraps. Engineers come up with weird things. So whatever the average voltage is on these inputs, and we don't know what it is because these signals might be balanced, they might not be balanced. But whatever the average is, we average it and we send it back as a reference to the volume control chip. And we've applied for a patent on this. We don't know of anyone else who's doing it this way. As I mentioned, these input voltages may or may not be the same. We look at this voltage on the input of the gain stage itself and send it back to the reference point of the volume control network. And back at the output here, we are left with our equal but opposite signals, which is what we want for perfectly balanced operation. All this is done with, as I said, a single amplifier stage. So we aren't relying on one set of amplifiers to give us variable gain and another set to do the sum and difference of the balanced signal. It's all happening in one stage. I'm going to go just a little bit deeper on this topic and discuss why this works. So again, in an ordinary implementation, so let's pretend that this bootstrap isn't here, it's not connected to the reference point. These are more detailed drawings of what the resistor networks and the volume control are. So imagine that there are multiple resistors with multiple FETs that switch the resistors in and out in different combinations. This is exactly how it works. There's this network and this network forming the one feedback element. There's this resistor forming the input portion of the feedback network, and then this portion which controls the impedance. What happens is, if our reference point is tied to ground, which is, again, this is how the chip maker tells you to use it, well, when we get out to here, this input and this input are not nominally at ground. There is signal there. So if we have signal here, and this is referenced to ground, it means that the control voltage on these individual switching FETs is varying with the signal. They're supposed to work like switches. They're either supposed to be on or off. But if the signal's varying, now they're acting like imperfect resistors. So the switching it's not ideal. So what we've done instead is to connect this bootstrap to the reference point of the chip. So now, whatever the average voltage is between these two inputs, that now becomes the reference voltage instead of ground, which means that the control voltage on those FETs is almost perfectly constant, regardless of what's coming in. So, what does all that mean? Because that's a lot it's a lot to absorb. I'm available for questions later, or now if I've been completely unclear. What does it mean? So, with a balanced input signal, this is what our signal and distortion spectrum look like. So you can see there's a little bit of third harmonic, a little bit of second harmonic, but not too much. You know, this is minus 120 dB. So it's pretty clean. If we were to implement the volume control with the grounded reference point, but with a single-ended input, so an RCA input, you'll notice we have a bunch of second harmonic distortion. Now, it's still pretty low. It's below 90 dB, but it's not optimal. However, with our bootstrapped reference, you'll notice that our second harmonic is now back below 120 dB. We do have a little more third harmonic, but that's below 110 dB. So that's really quite low and a considerable improvement over this. So it means that, again, regardless of balanced input, single-ended input, doesn't matter. You're getting good performance and you have a much simpler audio path. Does that make pretty good sense? Okay. So one more technical topic, I promise, and then we can move out of the land of technical topics. So this is the second patent that we've applied for. It's the design of a unity gain buffer. So in other words, the voltage on the input and output is the same. However, the current that's available on the output is much higher than what's available on the input. And this is an important component of an amplifier because usually the element that does the amplifying is a resistor, which has, in a typical gain stage, a pretty high value of resistance. This buffer is what's called a diamond buffer because if you look, it's sort of a diamond shape to the signal path. Two complementary bipolar transistors drive two other complementary bipolar transistors. Output voltage equals input voltage. Now, if we look at that in terms of its equivalent circuit, so in other words, transistors aren't perfect transistors. They have resistance and capacitance associated with them. You don't want it, but you have no choice. It's the world. It's a nasty place out there. Parasitics exist. This is what we have. So we have to design electronics to work around that. So this equivalent circuit, you would be feeding the input with a pretty high resistance because this is what's in the previous gain stage. It's typically 10 to 100,000 ohms. There is capacitance associated with these terminals in a transistor. It's all transistors. It's life. So you'll see it here. We see it on these input devices. It's inherent. But what it means is those capacitors and this resistor form a low-pass filter. You don't want the low-pass filter, but sorry, folks, you got it anyway. And this affects the bandwidth of the circuit. How do we improve this? Well, there's a couple ways of improving it. This next circuit is something that, in fact, was used in some of the older Mark Levinson preamps. I know this was in the 326, if you're familiar with that unit. What we've done, instead of connecting the collector terminals of these input transistors to the power supply rails, we've instead connected them to the outputs of the buffer. So what does that mean? It means that instead of this voltage being constant and this voltage being signal, this being the signal voltage here, now the voltage at this terminal is also the signal voltage. So imagine now that all three terminals of this transistor are moving up and down in perfect unison with each other. So if the voltage here and the voltage here doesn't change, these don't change with respect to each other, it's as if that capacitor doesn't exist. You can't charge a capacitor if there's no change in voltage happening across it. So by doing this, it's as if this parasitic capacitance doesn't exist. Now you may well ask me, what about the parasitic capacitance out here? You're not doing anything about that. Well, no, we're not. But the resistance here is typically 10 to 100 ohms. It's very small, and this combination of 100 ohms with a few picofarads has very little effect on the bandwidth. This is really where the action happens. How could we make this even better? So this is what we've applied for a patent for. What we've done is we've added another pair of transistors in parallel with this pair. Now there's one pair that connects to the output state, or to the output, provides the signal to the next stage. This second pair of transistors is what is driving the collector terminals on the input transistors. So this is yet another implementation of a bootstrap, because this device is pulling up this terminal and this one is pulling down that terminal. So again, on the input side, because all of these terminals on those transistors are moving up and down in perfect unison with each other, we've again canceled the parasitic capacitance here. We still have the parasitic capacitance out here. Again, it's not as serious a problem because this resistance value is typically very small. But by separating these two load requirements, in other words, by having one set of transistors to drive these transistors and another set to drive the output, we have less interaction between the load and the input devices. So what does that do for us? Here are frequency response plots of the three versions. So the first one that we saw, the regular diamond buffer, starts to roll off much earlier than the rest. Now again, the scale here, this is 10 megahertz. So not that this is exactly audio frequencies here, but our experience has always been to push bandwidth as wide as we can. The first improvement, that diamond buffer, just with the simple bootstrap, you can see the bandwidth is quite a bit better, but there's this peak out here. And that sort of slightly underdamped response, frankly, tends to not sound very good. It can sound harsh, even though this peak is very high in frequency. However, the device that we've applied for a patent on, you can see, does not have this peak, and in fact, its bandwidth extends out well beyond the original improvement. Now this assumes 100K for the input resistance, and then a 1K and 1000 puff load on the output side. So these are pretty typical test conditions. This is a very realistic usage for this kind of a device, but a great improvement. So, end of the technical portion. We'll talk a little bit about the unit as a system. What's unique about this is the analog and the digital circuit boards. Each one is capable of functioning by itself. So in other words, the digital audio board can select digital inputs. It can drive headphones. It can drive the power amps. It can do all these things by itself, as can the analog board. The modular nature of this means that when our manufacturer is building a 5805, they install another circuit board, they change some hardware, and voila, it's a 5805. If they don't do that, they build a 5802. All the parts are the same. They're literally the same, but just fewer of them. So much easier from a manufacturing standpoint. What's unique about this product, though, the signal path is more direct. Because each one of these elements is able to function by itself, there's no need for example, for the digital signal to run through the analog board or vice versa. So in fact, what we have, this is just a rough block diagram of our digital audio board. So our USB input, of course, is run by our XMOS processor. We have 3 SPDIF inputs. We may run those signals through the XMOS processor or not, depending on whether we do upsampling or MQA decoding. We have our 9026 Pro D to A with 4 I to Vs. That goes through some pretty sophisticated output switching so that it directly drives the 2 amp channels. The same happens with the analog board. So we have our moving coil head amp, our moving magnet amp. So you can use either. The moving coil amp, of course, uses both. Our EQ, the line inputs go directly into the line stage. And again, if you've selected an analog input, it goes directly to the amp channels. So let's talk a little bit, kind of wrap this all up. How did we do on our feature checklist? So let's see. Our analog preamp, yeah, we added all those features. We have MQA, we have Bluetooth, we have the amount of power that we needed. All of this control stuff, we hit our price target. What didn't we do? Well, we didn't do 32-192 or double speed DSD. Sorry, instead we got 32-384 and quad DSD. So happily we did better than we promised we would do. And we were also able to add user selectable upsampling. It's another one of those things like a digital filter. There is no right or wrong. Some people prefer the upsampling, some don't. So at the end, we were left with this. So as I mentioned earlier, you remember the rendering that we saw from Harman's Industrial Design Department? Well, this is a photograph. This is not this is no longer a rendering. And it looks pretty darn close to what we started with. But at the end of the day, we met our design goals, and I believe we exceeded what we thought we could do for performance. And that is the end. Are there any questions? It actually sounds better this way. I'll share an experience with you. When we were working on the number 519, one of the things that we did was we decided, let's give an end user the option of using the volume control in the D to A converter. And we thought, well, it's not ideal, but why not? Maybe someone doesn't want to buy a preamp. Frankly, we did that. I listened to it, to a prototype, to make sure that it wasn't awful. Not only wasn't it awful, it really sounded quite good. So by doing I'll go back to the block diagram. By doing these separately, it also makes it easier to build the digital-only version because we don't require an analog board to do the digital-only version. And if we wanted to, although there's been zero demand for it, we could do an analog-only version. But this way, we have flexibility. It's good for manufacturing, and frankly, it sounds really good this way. It is. In fact, the amount of capacitance there is designed for 4 ohm operation to be able to support 250 watts at 4 ohms. So that's For an amplifier of this power rating, that's quite substantial. That's exactly why. If we have, this is another instance where we had to be mindful of the cost. So the heat sinks on the outside of the unit look manly, they look very nice. They're very expensive. They require a much more labor-intensive finishing process, and by putting the heat sinks inside the unit, although they still look good, we still do a nice finishing job on them. From a manufacturing perspective and a cost perspective, it's less expensive. The ventilation is still very, it's quite adequate. If you get a chance to look at the unit in person, I'm trying to see if we, yeah, you can't really tell from this photo, but the vents in the top cover are exactly aligned in between the heatsink fins. So there's a very good pathway of air through the fins in the heatsink. There's very little that I can share with you. If you're able to visit us in Hall 4, we're previewing a new product in addition to these. It's a CD, SACD player, the number 5101. That's coming probably the end of this year. And there are several other products in this series in development, but I can't tell you what they are. I could, but it would be trouble for all of us. Nobody wants that. Not like Proceed. One of the things that has happened, which occurred about a year and a half ago, the luxury audio group in Harman acquired Arcam in the UK, and Arcam for years has been a well-respected manufacturer of much more value-oriented two-channel and home theater electronics. So in that sense, I think the next sort of more value-oriented products would be Arcam. But there aren't plans to do that with Mark Levinson. It's good to have someone with a lot of history. Thank you. Any other questions? So if you think of anything, I'll be here for a little bit, but otherwise I appreciate everyone's time and enjoy your show.